Hi everyone, welcome to Deep Learning Talks. We're going to talk about logistic regression today. So, I've always wondered where should logistic regression fit in the whole modern AI world? In today's modern AI, we only talk about transformers, large language models, agentic AI. But where does logistic regression fit in all of this picture and why is it relevant? Should we even study? And if we have already studied it, how should we use logistic regression as a lens to view other neural networks and to maybe make sense and connect the dots looking forward, right? So, what exactly is logistic regression? The equation in logistic regression says that it's nothing but a weighted sum of inputs along with a bias, right? So you do W transpose X plus P, or sometimes we also call that equation as Y is equal to MX plus C, right? It's a linear equation, and we couple it or pair it or encapsulate it under a sigmoid function. So sigmoid function is used for the very first time here, at least when I started logistic regression. So I saw sigmoid for the very first time. It is nothing but an activation function. So what role does it play here? What role does sigmoid play here? Sigmoid naturally adds nonlinearity to the model, not to the data. And sigmoid helps us model everything as probabilities. So the output between negative infinity to positive infinity is squished between 0 to 1, right? So that's why we can view it as a probabilistic model, as a probability estimator, right? So I like to think about logistic regression as a neural network with a single neuron and no hidden layer, right? So it makes sense to me. Why? Because a single neuron, which is tied up or encapsulated with a sigmoid function and a summation function, it takes an input which is coming from the left hand side and getting into the neuron, and it does a weighted average or weighted sum of all the input along with the weights that are sitting on the edges of the neuron, right? And maybe adds a bias and produces output before you know before feeding it into a sigmoid, right? Or after produces an output after feeding it to the sigmoid, right? So this is what logistic regression seems to me: a simple neural network with one neuron and no hidden layer. There is the concept of activation function W transpose X plus B, which is the same equation that we see in neural networks, which is also an equation that we can see in linear regression, right? So that the same equation is very persistent here, right? And the idea of activation function is also persistent here. So for me, logistic regression is a simple lens to view a neural network, right? Now, what about a neural network? Neural network is stacks and stacks of these neurons, stacked horizontally and stacked vertically, and connecting all the edges from the left and from the left to the right. So we have a stack of input layer, then a stack of hidden layer, then a stack of output layer, right? And each neuron can be seen as a simple logistic regression equation or a simple logistic regression model. The idea of activation function remains the same, right? Now, what about the loss function? Here we are trying to minimize negative log likelihood. We are trying to use something known as binary cross entropy loss, which helps us perform classification problem for two classes. It helps us answer true or false. It helps us answer yes or no, right? So the same loss function, which is binary cross entropy loss, can be generalized for a multi-class classification or a k-set classification problem that we naturally see in all neural networks, right? Now, what about optimizing this loss? What about optimizing the whole function with the data? We have the same concept of learning rate and the main best transient concept that we have always heard in deep learning, which is gradient descent. We differentiate the loss function and we keep on doing it iteration over iteration, and as the delta which comes after the partial derivative, we use that delta to update the parameters, right, in the right direction. So when we update the parameters and we do it over and over again, and we do it for multiple iterations, this is what gradient descent says, right? So now what about the loss function? So the loss function that we use here is binary cross entropy loss, right? So binary cross entropy loss says that uh, I will help you minimize the negative log likelihood. I will help you take a probabilistic decision between yes and no, right? We don't use mean squared error here. We use something known as binary cross entropy loss. Now, this binary cross entropy loss can also be stretched in case of neural networks to solve k-set classification problem. Here we are using the probability model to solve two-class classification problem, and we extend it to perform k-set classification problem. Right now, the same loss function is very much persistent in non-neural networks whenever we want to solve a classification problem. So that's why logistic regression introduces us to some of the concepts that are very long-lived and that are not isolated and only connected to logistic regression. Now, what about optimizing this loss function? How do we find the best values of W's and B's? In the W transpose X plus B, I want to find out the best values of W's and B's. What is my best bet? So my best bet to find the most optimal parameters is obviously gradient descent. Gradient descent asks me to find the partial derivative or differentiate my loss function. And every iteration use the delta to update the parameters in the right direction. And if I keep on doing that over and over again, I will be able to find my most optimal parameters. And then I can converge. Then I can take a pause. I can either converge when I stop improving, when I've reached the global minima, or I can stop converging when I have maxed out my number of iterations. And I take help of learning rate. Where do I take help of learning rate? I use learning rate as the multiplier effect, as the the quantity or the scale with which I want to update my parameters, right? So this lens or this mental model where we view gradient descent that we learned in logistic regression, we view sigmoid as an activation function, and we view binary cross entropy loss as permanent fixtures or permanent pillars in deep learning, right? Along with this, we also view W transpose X plus B as a permanent pillar to understand a complex neural network, right? Because here we are trying to model or frame the idea of a single neuron. Once we understand single neuron, which is the smallest subunit of a neural network, then we will be able to understand or extrapolate it into a bigger neural network. Once we understand deep neural networks or bigger neural network or feed-forward neural network, we can pair it with the idea of convolution, we can pair it with the idea of attention to understand more and more nuanced and complex neural networks like convolutional neural networks or transformers, right? So this is my idea of understanding logistic regression, and this is my mental model for understanding logistic regression, and why I think it's super, super critical to know it way before you know deep learning.